specifically balancing robots or some kinds of robot that moves following a line, which is also a very early level. But after I moved into something more sophisticated, like neuroprosthetics, where you finally combine the robotic part with other parts also, like biology, chemistry, and all the other mechanics things you can find. So this is a more cross-disciplinary approach where you apply the embedded system on a certain field which is not very related to embedded system. And in this like 1, 2, 3 step, now I've reached this point where I'm able to take the setup of the embedded system and apply it to other fields. And to begin with, we have to understand what is an embedded system. Like people say embedded system a lot of the times. Even I personally did not have a clear idea what is an embedded system actually. So it is a computer designed for a specific task, not a general purpose task. When we talk about a PC or a laptop or some kind of devices like Mac, etc., these are the things that is for general purpose. But embedded system is not a general purpose thing. It can work as a general purpose thing, but it is not designed for that purpose. We design it for one specific purpose, and is generally very resource constrained and time constrained environment where we have to work with limited resources, limited space, and limited time. And it consists mainly of two things: hardware and the software. The hardware will generally have the microcontroller unit, the microprocessor, sensors, actuators, the power supply, these things. And the software will have the firmware, the real-time control, the communication stacks, which will have the I2C, SPI communication. I2C and SPI is used for the sensors, whereas we have the UART communication for the LEDs. We have the USB communication for the communication between the PC and the microcontroller. Then we have the CAN communication with the motors. Like depending on different kinds of devices that we want to communicate with, we have different kinds of protocols for that. Then there is this real-time control system. For example, there are different kinds of real-time control systems. One of them is FreeRTOS, which I personally use. And this system lets you define task and schedule task and handle the task itself. There is an interrupt, and then there is a scheduling of the task itself. So by using these two things, you can schedule task, and you can also use different tasks on different core of the system. For example, a very small microcontroller like ESP32, it has two cores, so you can schedule tasks on different cores at different times using this real-time control. It's like very essential system for any kind of microcontroller or embedded project. But there are also other approaches where they don't use this real-time control system. They use a more bare metal approach using a super loop. But those are more advanced level, and those are also very, very specific. But for general purpose embedded system, mostly real-time control system is used. And some key characteristic of embedded system, I've already mentioned some of them, like real-time or soft real-time constraint, which is true because when I work with IMU sensor, generally I have the frequency set to 1 kilohertz, which means that I'm getting 1000 data in just 1 second. So it's like a real-time data. Then it has to be energy efficient and low power design, and reliability, determinism, and safety, which means the system has to be reliable. The system has to like do what it's supposed to do. And of course, it has to be safe to use. And some real life application for the embedded system. If we look around us, everything we see and we use is in some way related to an embedded system, sometimes directly, sometimes indirectly. For example, on the micro level, we can see that smartwatches, home automation, maybe some automatic door, some smart fan, some smart light, all these things that we are using on a personal level, they are embedded system. They are examples of real life applications of embedded system. And on the other hand, at the macro level, we have entire industries which are run by embedded system. Like in the industries, we have the robotic arm, which is also an embedded system. In the healthcare sector, we have many machines which are using embedded system, like prosthetics. These are also embedded system. So as on the micro level, we have the personal items, which are embedded system. Also on the macro level, we have the big industries and big sectors. They are also using embedded system, which are driving the economy. So the real life application is really vast. And the more we go into the future, the more technology will come into our life, the more embedded system will spread to other sectors as well. Like nowadays, we're seeing remote control refrigerators. We are seeing smart light. What they're doing is basically they're taking a normal light, they're integrating an embedded system on top of that, and now you have a smart light. Now you have a smart fan. Now you have an automatic door. So as we go into the utopian future more and more, we will go into the embedded system, and the opportunities are endless. So at this point, I want to do a deep dive on two of my projects, and I have been very selective when I wanted to select which two projects I should use. And this project, the first one that I chose, this one is my kind of my introduction to embedded system, because this project taught me everything that I needed to get started. Like what is a communication stack, how to interact with the sensors, then how to uh, apply some algorithm like PID, what are PID algorithm, what is an actuator, and all these things that comes into the embedded system. So this part is really my beginning to the journey. And this project is about a balancing robot. So in a balancing robot, there are many different layers on which we work. So the at the most outside layer, we have the sensors, where we are using an IMU to get the data from outside. Basically, IMU stands for inertial measuring unit, and which gives you two kinds of data. So the first kind is the values of the linear force of three axes, x, y, z, and the second one is the velocity in the rotational axes of three axes, which is x, y, z again. So you get 3 plus 3, total 6 data, and depending on the frequency you're using, you get the 6 data. Maybe if you're using 1 kilohertz, it means 1000 into 6, 6000 data every second. And after you have this data, the next step is the control algorithm and the control system, without which nothing will work. In this stage, we are using a PID controller, which is like a basic one, or sometimes we're using a more advanced one like state estimator or sensor fusion algorithm to uh, finally find out how we can use this sensor data. We can filter the sensor data, and we decide what we want to do with this sensor data. And in the next step, we actually want to convert this algorithm outcomes that we have into actionable works, which are actuators. So now we are converting the outcomes of the control algorithm into the outcomes of the motors and motor drivers, which will actually drive the robots. And all these things, all these three steps are controlled by the embedded firmware and the real-time loops, which means that at every stage, the sensor, the control, and the actuator, which one will work first, which task gets scheduled in what way, all these are controlled by the real-time operating systems using the interrupts and all the task scheduling and all the other ways. So all these three steps also are part of the embedded firmware. And these are some of the components I want to show. So the first one at the top we can see is the IMU, which I personally use. This is from the ST Microelectronics. The second one is the motor driver board. This is a servo motor. This servo motor with the motor driver board. And the third one, like the big one, is a is a microcontroller board. This is a STM32 Nucleo board. And this one is also a board that I used extensively in my project. And one fun fact is that I recently had a couple of interviews with ST Microelectronics, and I have been doing like HR interview, then technical interview, and I'm at the last stage. And I don't have the result yet, but I hope I'll get in for an internship. Let's see what happens. So the second one I want to do a deep dive on is the biomedical project I did, which is focused on neuroprosthetics. And this project is actually part of the team I founded, which is the Polito neuroprosthetics team. And in this project, also the first step is always the same, which is signal acquisition. And here we are using electrodes, EMG or EEG, depending on what kind of things we want to take. For example, EMG is electromyography. So if we need the data of the muscle signals, we'll use an EMG sensor. And if we need the brain signals, we'll use a EEG sensor. Also, electrodes they are doing another kind of thing. So in this way, we are first taking the signal from the outside environment, and then we enter the signal processing. So basically, signal processing has many parts. The first step is always filtering. We'll use, of course, a low pass filter, a high pass filter, depending on what kind of filtering we want. Then we'll boost the signal. We'll do the feature extraction. And then we have the actual signal that we want, uh, which doesn't have any outside influence or any noise. We don't want those. So after we have the exact signal we want, we'll do a mapping with the exact things that is an actionable outcome. For example, we are taking a signal from the brain, and at this stage, we will write the code how that signal will get mapped to a movement on the robotic arm that we have developed. So at this step, we are actually uh, analyzing generally a lot of data, a lot of signal, and using the previous statistical analysis, we're mapping each signal to each actionable outcome. And this is also used for like speech therapy. For example, if someone doesn't can't speak, and you need to have some devices that will say the words that guy wants to speak. So what do? You see the signal, you clear the signal, then you have the signal and you map the signal to a word. And in this way, you create a dictionary of words which correspond to a signal. And after you have the dictionary or the database, next up, when something comes up, you know how to convert it. You see the signal immediately, you can convert it to a word and which the word will come out. So this is like a simplification of the process, but approximately it works in this way, but it's a very rough simplification. And my approach to this whole project was to make it an open source. That means that everyone can go in and see the code, because generally people are very skeptical when it comes to neuroprosthetics, because there is some aspect of privacy which is getting hampered. Like, how will you let someone take a look inside your brain and take the signals from your brain and take the data? It feels very, what do I say? Like, it feels very invasive. It's a very invasive technology. So it's important that the codes are open source, so people can go and see that their data is not getting stolen, their data is getting used in a good purpose, and the codes are out there. The whole method is out there. And also, we wanted to use some things like printing the parts on 3D printer to reduce the cost, to make it more affordable for people. And currently we are working on some models, some prosthetics, which are at our lab at the university. And we also have published a paper on this thing, on our approaches. If some people are interested in these things, maybe I can share the link and we can talk more about this thing. Okay, so this is like a rough map of how things work with neuroprosthetic. There is an implanted microelectrode arrays where we are taking the signals from. Then we have different things happening, like here we have the computation of 3D movement trajectory. Then we are control, like we are computing this thing into some real-time interface that is implemented on the arm itself. So this is like a cycle that works in this way, in this circular way. So now we are at the future trends for the embedded system. And as with everything nowadays, AI is everywhere. Artificial intelligence and machine learning, they're taking over all the sectors. And sometimes it's very comparable, sometimes it's not very comparable. But the good news for embedded system is it's very, very comparable. And like, I don't know if any sector is more comparable than embedded system with AI, because now we have edge AI and tiny ML, which are running on microcontrollers. And these devices are revolutionary. It means that you don't need a big data center and a big AI. You can just run local models on very small and very low resource devices. And you don't need a centralized control. You can have a decentralized control. If you want to have some API on your refrigerator or a smart light, you don't need to connect it to a data center like halfway out of the world in China or someplace. You can just have a local model, Edge AI or Tiny ML, which is running on the microcontroller, and it's like local control. You have your privacy, you have your like it's a non-invasive process. So it's like a win-win situation in both cases. But of course, there are limitations because when you have low research devices, it cannot perform as much as like a chat GPT or some big big ML model. Then more powerful low power MCUs and heterogeneous chips which are coming again. There are chips which are coming which are low res, and these chips will be powered by itself. Like it will be so low powered and it will have solar capabilities that you don't need to power it anymore. The chips will power itself. And IoT plus cloud integration for telemedicine and remote monitoring. Yeah, like there is a new revolution in the cloud technologies also. There is Amazon Web Services, Azure, like all these things are coming. They are also comparable with embedded systems. Then we have the neuromorphic and energy efficient computing. This is also related to the biomedical sector. And now let's get into some practical part. So how to get started and where to find the resources. This is like some questions everyone has. I myself also had those questions like, okay, I'm motivated now, but what to do now? How do I proceed? So basically, the thing is very simple. Just start with step one. Start very small, but start very strong. Blink an LED, read a sensor, build a small project, build something that you can deal with. Now there is projects on the YouTube, on the like everywhere there is resources. Take some small project that you can implement by yourself and do it by yourself. Take inspiration from other codes, but don't copy the codes. And I would suggest not to use the AI. Build project by yourself. You can make mistakes, and it is important to make mistakes because when you do the debugging, you will understand that how it is important to just stay with your code and try different things. So try it and try it like at least 2 times, 3 times, then use the AI. And don't just take all the codes from the AI because nowadays it's very easy. It doesn't make sense for a lot of people to just work on this. But trust me, like as someone who has worked on the low level for a long time, and not a long time, like my career is not like 10, 12 years old. I'm just 22 years old. So like when I say long time, I mean 3, 4 years. So as someone who worked in the AI in the low level for a while, I think it's much better to just try to do things by yourself, learn it, then you can do the AI integration. If you do the direct AI integration, you don't learn anything. So it's not very efficient. But when you know the things, then you can use the AI. It's not a problem. And languages, so C or C++. One of them is very necessary, and I would suggest C. For me, it works much better. But also C++ gives you some other edges. And then there is the basics of Python, because when you go at the high level, when you are working with something like computer vision, or like you are using some robot operating system like ROS1 or ROS2, then you need the Python, and also a bit of bash scripting like Linux or those things. And then the boards. Okay, there are the boards like STM32, ESP32. Then there are the development boards like Arduino. Then there are also microcomputers like Raspberry Pi 3, Raspberry Pi 4, Raspberry Pi Zero. Pick something that you can start with. Like for me, I would suggest ESP32 is very good. It has a dual core PC. It comes with ARM Cortex M, and this is actually a very good processor, and you can find it very cheap actually. I think here I can find it for €2, so it's not very expensive, and it's very good, something that you can get started and do a lot of things. And maybe when you need more AI capabilities or something else, you can move on to STM32 based ones like nuclear boards or something like that. And also, yeah, you guys are already ahead because you are here at the IEEE Society. So you are already ahead of the bunch. Do some hackathons, participate in open source projects, participate in any projects you want, find the things that make you passionate on, like inside the embedded system, find which side you want to develop on. For me, it was neuroprosthetics and like neuroengineering. Find which one you like, then specialize on that one. And at the end, okay, is closing and Q&A. Thank you very much for joining and listening to me for about 22 minutes or more. And there is my contacts, my LinkedIn, my GitHub, and there is an open invitation for everyone participating to collaborate on the neuroprosthetics or robotics projects. We are always open, and we are looking for brilliant students who can contribute to our projects. You can send me a message on LinkedIn, or you can send any request on GitHub, and we are very open. Okay, thank you. It's all from my side.
Thank you so much, sir, for deeply insightful. Thank you so much, sir, for that deeply insightful and engaging session. Your words have truly broadened our perspective on how embedded systems are shaping industries and driving modern technological solutions. Before we move forward, this is a reminder for all attendees that the link to register for your e-certificates has just been shared in the chat box. Please make sure to fill out the form within the next 15 minutes, as it will only remain open for that duration. Now we will open the floor for questions. If you have any queries for a speaker, please drop them in the chat or raise your hand, and we'll be happy to take them one by one.
Mahdi, I just have a little question. Like, what are the boards used in embedded system? Like ESP32 and more. Which boards are you using in embedded system?
Okay, so thanks for the question. And this is actually a very important question when you are getting started, or when you are at, I don't know, at like some stage, what kind of boards you want. So ESP32 is a basic board which is better for IoT projects, and which is also good for low resource projects, and which has some kind of real-time operating systems. Uh, but this is not very powerful board. So if you want to work on something like robotics, it's better to go with STM32. And if you want to work on something on IoT, like you want to create something smart home system or some smart light, ESP32 is more than enough. Again, and for the like robotics part, STM32 is better. And STM32, there are many different kinds of board. Nuclear board is a good starting point. And if someone wants to focus heavily on computer vision and AI, then there is another option, which is to go for a Jetson Nano, which is more advanced for the AI front, and it lets you use a real-time operating system. You can use ROS2, different versions of ROS2. You can use a Linux distro like Debian, or even Ubuntu. So depending on your need, there are different boards that you can use.
We have a question in the chat box from Saddam Hussein. He says that he's working on home automation project and wants to use cognitive automation. How to go through?
Okay, so home automation project I can understand, but cognitive automation is like a big project, and I don't know what specific thing you want to learn from. But if you want to know how to go through the cognitive automation process, you can find resources on like YouTube or GitHub. But I would be happy to discuss it maybe if you can send me a link. But this is not a topic that can be like explained in just some words.
Mahdi, can you explain why we use Raspberry Pi and FPGA except ESP32?
Okay, so FPGA is a field programmable gate array, and this is used for some purposes like when we have some automobile system, when we have some aviation system, and we need to directly implement the logic gates. Then we are using the FPGAs. And compared to that, STM32 and ESP32, they're more like embedded systems and embedded project, and they are using a software which is a firmware for electronics in uh, in uh, in relation with the uh, like with the hardware itself, like the microcontroller. And ESP32 is like, as I explained before, this is a low resource device, which is more like more useful for small projects where we need the Wi-Fi and the Bluetooth. Because one thing I forgot to explain is that the ESP32 itself comes with built-in Wi-Fi and the Bluetooth connection. So we don't need to buy those drivers separately and connect them. So this is a good thing, and this is a very good thing for IoT and some form of automation. But STM32, on the other hand, it comes with a lot of capabilities and a lot more powerful device, but it doesn't have those modules built in, and you have to buy sometimes those Wi-Fi modules and Bluetooth modules and connect them with the STM32.
Next question is from Muhammad Shahid Ali. He says that he's a telecom engineering student, first semester, and he wants to know how he can connect with you to get some skills.
I would be happy to connect with you. I give the link for my LinkedIn. You can come and say hi on my inbox. I would love to chat with you.
And
Okay, I'll
Saddam
drop
Hussein
my
wants,
LinkedIn here.
Saddam Hussein
I'll
wants to
drop
know
my
if he can
LinkedIn.
provide your email so he can discuss his project with you in detail.
Yeah, sure. I would love to. I'd love to discuss.
Next question is from Nadine Fatma, and she wants to know that she's an electronics engineering student, and are there any skills that you can suggest for her to, get into?
Okay, for electronics students, depends on first you have to decide where you want to go. Like, do you want to go into the farmer part where you're focusing more on the software and the coding, or you're going on the hardware part? Even in the hardware, there are sections like there is digital electronics. Do you want to specialize on digital electronics? Do you want to specialize on the analog electronics? So it depends a lot, but I would say at the core of it, just learning how system works and system design. This is a very important skill nowadays because AI is coming and just automating everything. So learning how things work is a very necessary skill. The second skill I would say is debugging. Is very important. Is debugging skill. Uh, if I spend like 2 hours writing some code, I will spend 3 days debugging that code. So for any kinds of electronics, a very essential skill is debugging. After you write the code, then you have to go and see what the problem is. Is the problem in the hardware? Is some connection is not working? Or the problem is in software? If in software, then where? In the C file or the Python file. So this is a very necessary skill, and you have like you develop some kind of intent after you do this debugging for a while, and you automatically know that the problem is in software or the problem is in hardware. So this intuition that you develop is very like important skill to have. And outside these two core skills, depending on what you want to specialize on, there are things you can develop like C, C++, Python maybe. Then there is also the design skills like uh, PCB designing, and AI is also essential nowadays, doing some machine learning with tiny ML or AGI, these things. Yeah. Okay, so I see another question that nowadays which microcontroller is widely used, and in the industry is STM32. Do you want me to answer the questions directly or would you read them?
I'll read them out for you. Next is from Nasser, and he asked that how is artificial intelligence being added to embedded systems in real-life examples, and does it affect the conventional embedded systems?
Okay, yeah, this is a nice question. Yeah, it does affect the conventional embedded system because the conventional embedded system is worked on a limited code and worked on like limited things. But when we add a artificial intelligence, it's not limited to the codes itself. It has a like a smaller brain, you can say. And how is it added? So there are things like TinyML. Then there are also like if you're familiar with TensorFlow, there are machine learning models which are TensorFlow Lite. So these versions you can directly deploy into an embedded system.
Next, Kamal Heather wants to know your opinion on whether electrical and electronics, between electrical and electronics engineering, which one leads?
Okay, so I would say electronics because electrical was a thing of the past, and more we're approaching future. I think we're transitioning more to the electronics. Even nowadays, if you see the electrical grids, which are completely the domain of the electrical engineers, they are having an automation. They have a SCADA, if someone is familiar with it. So the SCADA is like a controller through which you can apply the automation and control the electrical grid itself. And this SCADA is creating a domain for electronics engineers to directly work with the electrical grid. So the more we'll approach the big machines, we'll also have a computer-like controller. And when you have a computer-like controller, this is the domain of electronics.
Then Yakub would like to know that he is an electrical engineering student and working on machine learning projects. So where can he get some information on that?
Depends. If you wanna stay in the electrical engineering, then I really don't have an idea how that works because I am from electronics and telecommunication. But if you wanna go on the electronics side, then there are like there are sites. For example, there is Hugging Face where you can go and see all the models you want. I can even type it out for you if you want.
Next is that in neuroengineering applications, how do embedded systems interface with neural signals like EEG activity while minimizing noise and maintaining real-time performance?
Okay, so how do embedded system interface with neural signals like EEG activity while minimizing noise and maintaining real time? The first step, which is the minimizing noise, is you do this through filtering and boosting the signal itself. If you took some courses on signal analysis, I think you're familiar with low pass filter, high pass filter, band stop, band pass filter, and different kinds of filters like different kinds of like filters. Using these filters, we are removing the noise from the signal, and after that we are feeding that signal into the system and into the algorithm, and this algorithm will take the signal as the input and produce an output which can be converted as some movement in the motors, if you are talking about like robotics or whatever. And maintaining real-time performance. Okay, so real-time performance is maintained by real-time operating system itself. A real-time operating system is just like an operating system. but it's very specific for a task. And in a real-time operating system, you schedule the task. That task one will get performed in this time, task two at this time. This is called task scheduling. Then there is a concept of an interrupt. So when you have some outside influence, an interrupt gets called, and that interrupt will call the task, and the task will get executed. So in this way, using a real-time operating system, we are maintaining a real-time performance.
Next, Matt would like to know what is the benefit of using embedded systems in projects at the university level?
What is the benefit of using embedded systems in projects at the university level? What is the benefit? The benefit is like depends on you what you want out of it. You can learn something like from the doing the embedded system if you wanna go into embedded system or not. Maybe if you are doing the project for a lab, then you are doing for a lab. This is the benefit, I guess.
Hafiz Hamza Ikram would like to know that how to start embedded systems as a CS third semester student, and is it feasible to go towards embedded systems for a CS student?
Of course, of course. A lot of engineers who are in the embedded system, they're coming from the CS because a big part of embedded system is software. So you already have the software as a CS third semester student. So you need to have some idea of how hardware works. You need to understand how at the low level things work. Then there is the middleware, like how each task gets executed from the bare metal level to the application layer. Application layer is the layer on top of which normally the computer science students work. They work on top of the application layer. But you need to go deep inside and see what is below the application layer, what is below the middleware, what happens in the middleware, what happens on the bare metal layer, what happens on the hardware. Like, for example, what is a HAL? HAL is called hardware abstraction layer. So in many times, we don't directly interact with the hardware itself. We have a built-in layer called hardware abstraction layer. So we call the HAL and we interact with the HAL itself. So for you, I would suggest that understanding this layer, which are below the application layer, would be really helpful, and you can directly start working on embedded system.
Shahzad Mir would like to know that why we do not use ESP32 in industry instead of PLC, and can we use ESP also?
Okay, so yeah, this is true. Nowadays, mostly PLC is used, and one of the reason is that the cost is less, and also there are not enough people who are trained to implement ESP32 in industry. PLC is an old technology which are used in big machines like, for example, the big coffee machine where you can put your coin in and get a coffee, or some other machines used in the industry. PLC is very simple to implement, and you can train people easily. And it's also a technology that has been used for a long time, and it works. So now these things are not changed, but maybe in the future they will be changed.
Next question is that should we prefer Arduino coding in Python instead of C or C++?
I don't understand the question because Arduino itself has a coding language, and I think that that language is developed on top of C++. Maybe you are asking about the Arduino boards, like should we program the Arduino boards in Python instead of C, C++? And depends on what you want to do. If you want to apply some machine learning models, then sometimes I know that these boards allow you to code on MicroPython. MicroPython is like a simplified version of Python without the advanced libraries. So sometimes you are allowed to use MicroPython, and maybe you can use it. It makes easier to implement the high level things like AI or machine learning. But if you are doing some like low level stuff, so it doesn't make sense to use Python. You can just stick with C, C++. It's much easier.
Next
Okay,
is
next.
Wiki Lemon. He'd like to know, Sir, I'm working on FYP, military spying and bomb disposal robot. We are using ESP32, but its transmitter and receiver should be connected through one Wi-Fi modem. How to increase its range because Wi-Fi has limited range?
Okay, let me understand. Military spying and bomb disposal robot were using space, but can you not use some signal booster which can boost the signal? Or maybe you can use a different technology. Why do you have to stick with Wi-Fi? Maybe you can use LP1, which has much better range, when which is also low power and low resolution. Maybe try to experiment with some other technologies. There is LoRa1, there is LP1, and these kind of technologies. Okay, next.
The last question is, I'm an electrical engineering student in my 5th semester, so what kind of study to embedded system to gain a final year project and how to start first?
Okay, so there are two parts of this question as I can see. So how to start first? Starting is, I think, same for everyone. Start with some LED blinking. Try to play with LEDs. Try to blink different LEDs in a pattern. Try to take some sensor data. See if you can take some sensor data, like use a temperature sensor, use a humidity sensor, and see if you can take the data. And then use the LED to show the data itself. Like these are very simple things, but it will get you started. And after that, what kind of study to embedded system to gain a final year project? Okay, so for final year project, my personal suggestion would be go into Edge AI, try to integrate the embedded system with an AI, and this will be very good. Like use some API. There are some very good APIs now also in cheap prices if you buy from DeepSeek. So buy some API, use some API in your project, make it an Edge AI project, and it will be really awesome, I think. Okay, next.
One final question. Looking to the future of embedded system applied to neuroengineering, do you think we will achieve a true human-machine symbiosis where devices are not only able to read but also interpret and dynamically adapt to neural signals? From a hardware perspective, what advances in microcontrollers or embedded architectures do you think will be crucial to enable such applications?
This is actually very difficult to say that if we will achieve a true human-machine symbiosis, but maybe we can go closer to this thing. And I think the limitation does not come from hardware itself, because okay, there is some limitation in the sensors because the data is always corrupted that we're taking, but that can also be minimized using filters and some software system. But I think the limitation is more on the software level, and we don't have enough a powerful enough machine learning model or a powerful enough like software that can do this thing. And from the hardware perspective, I don't actually know what kind of advances in microcontroller or embedded architectures would do these things, because from my point of view, this is not a limitation, because what we have now is enough. I think the limitation is in the software. Okay, next.
I think that's about it. Um, Thank you all to our participants for the great questions and to our speaker for the perceptive answers. Before we officially conclude, I'd like to extend heartfelt thanks to our speaker, our IEEE organizers, and everyone who worked behind the scenes to make this event possible. And of course, a huge thanks to all our participants for joining us and making this webinar such a success. Have a wonderful evening, stay curious, stay innovative, and keep the IEEE spirit alive. Allah Hafiz and take care.
Thank you very much, Shafak. Have a nice evening.
You too, Hafiz.